Okay, and you know that the rotational energy levels can be defined like this. So this rotational energy level E J, this will be equal to B J into J plus 1 centimeter inverse. Okay, and yeah, this is equation number 1, and the where J is the rotational quantum number, which is equal to 0, 1, 2, 3, and so on. Okay, so this expression will represent the rotational energy levels. Okay, so the what about the selection rules? Transition between these levels is followed by the selection rules. So in this case, the selection rules will be now selection rules. Here, selection rules are going to be delta J will be equal to either 0 or plus minus 2. So you can see that in the pure rotational spectra, if you see the rotational spectra, okay, or in the microwave spectroscopy, in microwave spectroscopy, rotational spectra selection rules are delta J plus minus 1. Okay, so we have seen in the case of this rotational spectra that the selection rules are plus minus 1, but here in the case of Raman rotational spectra, the selection rules are going to be delta J 0 or plus minus 2. Okay, so uh, actually why this plus here. So here, in the Raman case, the plus minus 2 section rules is very important in the sense that these 2 unit change in the energy levels is described in terms of the observation that when the linear molecule is rotated end by end, okay, if there is a end by end rotation of the linear molecule, for example, we have any linear kind of molecule, if you rotate this molecule end by end, okay, end by end means like this, end to end rotation, okay, end to end rotation. If you do this end to end rotation in linear molecule, what happened to the observer, it will be seen by twice in a complete rotation, end to end rotation. Observer C can see twice in a complete rotation. Complete, you can say end by end rotation. So what was the idea behind this the plus minus 2 section rules, that when this linear molecule is rotated end by end, so observer can see in a complete rotation, it will make observers see that molecule twice. That's why the plus minus 2 change in the angular momentum is considered in the pure rotational Raman spectra. Okay, and other thing is same. So here let us see when you find out is delta J actually. In the delta J, so delta J is basically the J upper state minus J lower state. Okay, J difference between the upper state minus lower state of the rotational quantum number, J upper minus J lower state. Okay, so if I take so this delta J is zero transition. This is again a tricky one. In delta J equal to zero transition, actually, it will represent no change in the molecular energy levels. Okay, but it is basically, if there is no change in the molecular energy levels, it will be regarded as Rayleigh scattering only. Okay, this will regards as Rayleigh scattering. No change in the energy levels. So particularly here, means two rotations are important in the case of the Raman rotational spectra. Now, if you take delta J plus 2 and delta E, you can just write change in the energy like this. Delta E is equal to E J dash equal to J plus 2 minus E J dash equal to J. Difference between these uh, two energy level, let us put J dash equal to J plus 2. So you can put here J plus 2 in question number 1, then J, and try to find out the difference. So you will see that when you put J plus 2 and J in the question number 1, you will see that it will be equal to B, this will be 4J plus 6 centimeter inverse. So the change in the energy will be equal to B 4J plus 6. J is the rotational quantum number, B is the rotational constant basically. Okay, and you know that in one of the lecture we had discussed that there are some branches. So these levels, these spectrum are rotational spectrum are divided in terms of branches depending upon the rotational quantum number. So this J equal to plus 2 or minus 2, it will represent the S branch. Okay, J equal to plus minus 2, this will represent the S branch. It is designated as S branch in the spectrum. Okay, so there J plus minus 2, it will represent the S branch of the spectral line, so that I can just write this as delta E change in the energy levels. It will correspond to the S branch. Delta ES will be equal to B, this 4J plus 6 centimeter inverse, where J equal to 0, 1, 2, and so on. Okay, so it means that if the molecule gains rotational energy, okay, if molecule gains rotational energy from the photons during collision. So what was the theory of that quantum theory of the uh, this Raman spectrum, that there is a photon, light can be represented in terms of photon. That photon is interacting with the molecule. When this interact with the molecule, the molecule, this photon can gain energy or it can lose energy. There can be two different possibility. Okay, and this will happen only when there is a inelastic collision between the molecule and the light photon. So this is the quantum theory basically. So based on it, if the molecule gains the rotational energy from from the photon during the collision, we have series of S branches towards the low wave number side, okay, which is called Stokes line. So let me just write here the molecule gains energy. Molecules gains rotational energy from photon. Okay, during the collision, as per the quantum theory of light. So we have the Stokes lines. Stokes lines, which will be towards low wave number side. This will be towards low number side. that S branches towards the low wave number side. Okay, if the and vice versa. If the molecule gains in the rotational energy, if the molecules lose. Okay, if molecule lose rotational energy to the photon during the collision, then there will be a anti-Stokes lines. This will be towards the high wave number side. So these are actually, these will be S branches. So we are talking about S branches here because delta J in this case allowed transitions are only delta J plus minus 2. Okay, so if I just draw these spectral lines, so it will be like this. So let me draw the spectral lines. So firstly, let us uh, draw these rotational energy levels. J equal to 0, J equal to 1, J equal to 2, 3. So rotational energy levels, like they will, the distance between the energy levels go on increasing when you increase the quantum number. So we had discussed this in the previous lectures when we were discussing about the rotational spectra in the microwave spectroscopy. So it will be like this. So this will be J equal to 0, 1, 2, 3, 4, 5, 6, okay, 7. Okay, so now there is the only possibility will be plus minus 2 transitions. Let me just write these transition with some. So we have here a center, so I can just write here. So one transition can be like this. 3 to 1, delta J minus 2, 4 to 2, like this. Okay, in the left hand side, means in the lower wave number side, we will have the transition like this: 0 to 2, 0 to 3, 1 to 3, sorry, 2 to 4, then 3 to 5, like this. So in the low wave number side, we have Stokes lines. Okay, these are Stokes lines. And towards the higher wave number side, we have anti-Stokes lines. Anti-Stokes lines. Okay, so when I just draw the spectra here, this intensity of spectral line, this will correspond to the 0. This will, at the center, we will have the exciting this. This correspond to the wave number, which is the excitation, at excitation actually. So I can just plot the spectral line like this. So corresponding to this here, it will be like this. So remember that when we were discussing about the rotational energy levels, so we had to find out the expression for the intensity of the spectral lines in the rotational energy spectra. Okay, so how was that? How this varies? It will, that varies like with increasing the J, increasing the quantum number. This was like this, no? So it was like this. So when you have this quantum number intensity, or you can say population actually. Okay, population of this population intensity, you can say. So it was like this. At one point of J, it will be maximum. After that, it will be like decreasing. Okay, so see, similarly here, it will be first for the increasing J, its intensity will go on increasing like this. At some value of J, it will be maximum. After that, it will be decreasing like this. Similarly, in the case of Stokes lines, so for the low wave member side, it will be firstly low intensity, then intensity will go on increasing, then it will decrease like this. Okay, so these are the Stokes lines. And these are anti lines. Okay, so one thing is important, that the a separation of the first line from the exciting line. So this is the exciting line. V excite. This is called. This is the exciting line corresponding to the incident wave, with the frequency of the incident wave, actually incident light wave. This is called exciting line. Okay, the separation of the first line from the exciting line, it will be 6b. Okay, if you see that, this will be this one. First line, it is actually 6b centimeter inverse. Similarly here, this line, first lines, whether Stokes line or anti-Stokes line, it is 6b. And means j is equal to 0. Okay, in this expression, if you put j equal to 0, you will see that it will be delta ES. Separation will be 6b. So let me just write here. If you put j equal to 0, delta ES will be equal to 6b centimeter inverse. Okay, then you can put j equal to 1, 2, 3, 4, so on. You will see that after that, the there will be a same spacing, equal spacing will be for all the lines, which is the 4b, which is the 4b. Remaining spacing, all these spacing will be 4b. Okay, these spacing are 4b centimeter inverse. So first spacing from the exciting line, it is 6b centimeter inverse, and the remaining spacing of the Raman spectral lines are 4b centimeter inverse. Okay, so that was the pure rotational spectrum of the in the case of Raman active. We can say pure rotational Raman spectrum. Okay, is actually simpler one, but there can be other spectrum like the vibration spectrum, then mixed kind of spectrum, rotational vibration spectrum in the case of Raman case. Okay, any query, any questions? Any questions? I hope I am audible.
Yes, sir.
Okay,
Hello,
so if any, hello,
hello, sir.
yes, yes, please.
Sir, here anti-Stokes and Stokes lines is showing like that when light is observing, this is this is like a this is like showing Stokes. I mean, when light is emitting, that is showing like a anti-shock. So this is correct or not, sir?
Okay. So yeah, so here what we are discussing, see, the Stokes and what are the Stokes, when the Stokes anti-Stokes, what was the definition actually? So when we are discussing the quantum theory of light, so when this photon interact with the molecule, okay, so this photon can give energy to the that molecule, or it can gain energy from that molecule. Okay, so when it gain energy, then this when this energy is gained by the molecule, so see here, if the molecule gains rotational energy from the photon actually, then it is a Stokes line. Okay, when it loses energy, it is the anti-Stokes. It is you are saying emission and absorption, na? It is not like that. It is like taking the energy from the photon or giving the energy to the photon. So Stokes anti-Stokes lines are basically represented to the giving and taking the energy from the photons. So that there is the rotational spectrum, and J is plus minus 2. For one case, it
Sir,
is
how
gaining
molecule
energy.
will be
Mhm. How molecule will be? Hello? Hello? You are not audible. Veera? Hello? Am I audible?
Yes, sir. Yes, sir. Due to network, it will be automatically closed, sir.
Okay,
Again, I
okay.
joined.
Yeah. So, yeah.
Sir,
What to? Mm-hmm. Yes, yes, please.
sir, how molecular will get energy from photon, but how it will be giving to energy to photon, sir?
Yeah, so see what we are discussing here, we are discussing the rotational spectrum. So when we are
Yes,
discussing
sir.
rotational spectrum, that we are assuming that the molecules are rotating. Okay, so during this rotation of the molecule, there are some kind of energy associated with this rotation. That is called rotational energy. That's what I was saying, that it is the, so see if molecule gains rotational energy, I'm talking about rotational energy. This is energy due to the rotation of the molecule. So see, any molecules, it will be rotating or it will be vibrating. Both can be happen at the same time as well. Okay, always these molecules are rotating or vibrating. So there are the rotational energy or vibrational energy already there in the molecules. Okay.
Yes, sir. Yes, sir.
Any other query? Okay. So if there is no query, then I can proceed further. This was the pure rotational Raman spectrum. Okay, where the section rules for the conjugate are plus minus 2. Okay, plus minus 2, they will correspond to the Stokes and anti-Stokes lines. Now, what about the vibrational Raman spectrum? Okay, this was the rotational Raman spectrum, vibrational Raman spectrum. So in order to discuss this vibrational Raman spectrum, firstly, we have to discuss about the Raman activity of vibrations. Okay, see how the Raman mode are active in the case of vibrations. So let me just discuss this. So I will take two different examples. So Raman activity of vibrations.
Sir,
Yes, please.
sir, is there any probability of Stokes line and anti-Stokes lines?
Is there any
Sir, probability,
probability? Okay.
because sir, as J value increase, the rotational energy of molecule increase. So in that case,
Hmm.
sir, Stokes line is more preferred.
So that's what I was saying, that in the case of the rotational spectrum, the probability is like this. Na? So when you increase this J, what happened at a particular value of J, this probability, or you can say population, you can say the intensity of that particular spectral line will be maximum. Intensity is actually proportional to the probability of the transition. Larger the probability of transition means higher the intensity is. Okay, at a particular value of J, it will be maximum. Okay, as a particular value of J, it will be maximum, but after that, when you further increase this value of J, its probability or population or intensity, you can say it will be decreasing. That's why I have shown here that the intensity close to the exciting line is lower, and they will go on increasing at a particular value of J. Okay, but after that it is decreasing like this. Okay. Okay. So this will be probabilities
Yes.
gone by this there was an expression we had discussed in the when we were discussing this rotational spectrum in the microwave spectroscopy. At a particular value of J, it will be maximum. After that, it will be decreasing intensity, or you can say probability of transitions. Okay.
Yes, sir.
So now the Raman activity of vibrations. So this is very, very important, and it is also very, very tricky one to understand or confusing to understand. Let us try to discuss this. So Raman activity of the vibration. So see what we have discussed in the case of the basic theory of this Raman spectrum, that the when there is an interaction of the light with the molecules, okay, what should happen during the vibration? There should be change in the you can say the dipole moment. Okay, when there's a change in the dipole moment, it means there is a possibility of the polarizing that particular molecule, or there is a possibility of the polarizability. Okay, so ability of the polarizing that particular molecule is given by this alpha, that is the polarizability, and basically these are governed by the polarizability ellipsoid actually. Okay, let us try to discuss that. So let us consider the asymmetric top molecule, simple molecule. Okay, let us take the example of uh, simple asymmetric top molecule H2O. Simple asymmetric top molecule H2O. So let us take the example of H2O molecules. Okay, so during for the Raman active mode, so there should be three different active modes for the vibrations. Okay, so one is called the stretching mode, another one is called the bending mode, and third one will be the asymmetric mode actually. Okay, so let me just describe these three different modes for the water molecule. I will be back. Okay. Yes. So you can take. So there are three different modes there. Okay. Let me just draw these three different modes. Okay. First one is the symmetric stretching mode. Stretching mode is like this. So we have, if you see the H2 molecule will be like this. Oxygen is here. Okay. Here is hydrogen atom. So this is bond is symmetric. It is equal. HOOH bond. These are same. Okay. This is the H2 molecule, and I am talking about the symmetric stretching. So what I am doing, I am just compressing this bond, OH HO bond. I am just compressing this bond, so it will be looking like this. So let me draw it with different color. So we have now oxygen here. Okay, so now this bond is slightly shorter because I have this stretched means compressed this bond. Okay, so now it is H. Okay, now the third possibility is that I can just expand this bond. So let me call this expansion of this bond is like this. Okay, so this mode is called the that is called let me call it as new one. This is called stretching, symmetric stretching mode. This is the symmetric stretching mode. Okay, so this was the original one, this one. Okay, so when you just compress, this is the compression mode. Okay, I am just compressing this. This is the expansion mode of bond. Expansion of what? OH bond. Okay. Compression of here OH bond. Okay, so in one hand we are compressing this OH bond, in other hand we are just expanding this OH bond. Okay, so if I draw the polarizability ellipsoid, polarizability ellipsoid for the H2O, it will be its shape was observed like this. Okay, so where there is some kind of dipole moment will be there because of the induced dipole. So it's here there will be induced dipole moment, and due to this induced dipole moment, what is happening? Charge is more charge is accumulating in the one side, less charge in the other side. That will gives rise to the dipole moment, and that dipole moment further gives rise to the polarizability in that particular molecule. And shape of that polarizable molecule is given like this. This is called the polarizability ellipsoid. Okay, this is polarizability ellipsoid. ELLIPSOID. Okay, during the compression, what happened? This polarizability ellipsoid, it will be slightly bigger in shape. It was observed like this. Okay, shape is going to be same, but bigger shape. This shape will be same, but size will be bigger. Okay, so again here, in the case of the expansion of this bond, this polarizability ellipsoid is like this, slightly smaller in shape. Smaller in size, sorry, shape will be same. Okay. So this is one mode of the vibration. Okay. New one mode. This is the symmetric stretching mode, where you stretch the bonds and the corresponding there will be change in the size. So what is happening here? What is happening? The change in the size of polarizability ellipsoid is observed. Okay, this is the first mode, stretching mode. Second mode is the bending mode. That is, you can just bend the molecule. Bending mode. Second is bending mode. Let me just write here. This is called new 2. This is bending mode. Symmetric bending mode. You can say simple bending mode. Okay, so bending mode, again we have the water molecule here like this. Okay, so you can bend this molecule by decreasing the angle between the HOH atoms. Okay, so one bending mode, compressing, means decreasing the angle. So it will be like this is angle. You can just decrease this angle. It can be like this. Okay, this angle will be decreasing. This angle was decreased in the one hand. Other hand, you can just increase this angle. So it will be like this. So this angle is increased. Okay, this is H here, H here. Okay, so corresponding the this polarizability ellipsoid, it will be like this. So initially, it was like shape was like this. So when you this compress this molecular angle, okay, if you compress this angle, so what happened to the size of so corresponding size, actually it will remains nearly same, volume will remain same, but what happened, the shape will change. So it will be like this, shape will be like this. And in that case, in the when you just increase the angle, the shape will be looking like this. So what is happening here in the bending mode, shape of polarizability ellipsoid changes. Shape of polarizability ellipsoid changes. So see, this is Raman active transition. What should happen? There should be change in the either shape, size, volume of the that particular ellipsoid. Okay. Third mode of this vibration is the asymmetric stretching mode. Okay, asymmetric stretching mode. This is designated like new 3. This is asymmetric stretching mode. So again, in asymmetric stretching mode, initially it was a molecule is like this, H2O molecule. In asymmetric stretching, what we are going to do, actually we are stretching one of the bond. Okay, we are stretching one of the bond, and we are just compressing other bond. So we are just stretching this OH bond. Okay, okay, and we are just compressing this bond. Okay, so it will be like this. In one bond we had stretched more to the original position. In other way it is like smaller one. This is asymmetric, you can say, the stretching. So in the other side we can have like this. So we have this in one side I have just compressed that bond, and other side I have just elongated that bond. Okay, if you draw the polarizability ellipsoid, so it will be like this, shape of like this. So what happened in this time is in this type of stretching, what happened, there will be a change in the major axis. Actually, direction of the polarizability will change. Okay, if initial direction was like this, direction of polarizability, what happened in that case, direction of polarizability will be like this. Shape size will remain same, but the direction will change. Okay, and here in
So
that
the
case
shaded
direction
portion
will.
is on the left side.
Mhm.
Sir, the shaded portion means higher charge is on the left side.
Yeah, yeah, you are right. Because the charge will be the accumulated in the longer side of this bond. Let me just write. Yes, yes, please. Tomorrow. Okay. So similarly, in the other way, shape and size will be same. Okay. You can draw the equal size and shape of these uh, ellipsoid. So what is happening? There is a change in the direction. Here in this stretching mode, what happened? There will be change in the direction of polarizability. Change in the direction of polarizability. So in the three different modes, what is happening in the first mode, when there is a asymmetric uh, stretching, there will be change in the size of the polarizability ellipsoid. In the second case, in the bending mode, there will be change in the shape of the polarizability ellipsoid. And in third case, there will be change in the direction of the polarizability. You can say ellipsoid. In all the cases, what happened? They will represent a Raman active modes. All these three modes will be Raman active. Okay, all these three, new one, new two, new three, all the three modes are going to be Raman active in the case of hydrogen H2O molecule. Okay.
Hello, sir.
Yes, yes, please.
Sir, is there any chance to means to mix with two mode like stretching mode and bending mode?
Is there any chance of
Mixing of two mode, stretching and bending mode.
mixing of two modes? In what sense you are saying that?
I mean, sir, if the bond is compression and there is compression and expansion, and along with that, there is change in angle.
Okay, so this kind of, you can say, you are saying that at the same time stretching is occurring, at same time the bond
Yes, sir.
angle is also changing. So this type of possibility will be very narrow. So corresponding lines, if you see the Stokes lines, no, Stokes anti-Stokes lines, Raman's lines, it will not be observed in the spectrometer. So most prominent one which will be observed in the spectrometer will be like this stretching mode, bending mode, and the third one is this asymmetric mode. Bending and symmetric mode is also observed very, very less actually. Its probability is very less. Most prominently in the case of water molecules, this stretching mode vibration, new one, it will be observed most prominently actually. So this can happen, means this can be, you are saying two modes can be combined, it can be three modes can be combined. Okay, but the intensity of prominent intensity in the spectrometer, it will be less, it will be not very visible in the spectrum. So we are discussing the only that part which will be actually significant in the spectrometer, no? That is, intensity will be given, that particular wave number. Okay, possibility is infinite there. Okay. Okay.
Okay, sir.
So this was the case of the H2O molecule. So we can say that all the three vibrations modes, this involves actually at least one aspect is changing. In the first case, this is the changing in the uh, size of the ellipsoid. Secondly, shape. Second case, change in the shape of the ellipsoid. In third case, the direction of the ellipsoid. In all the three cases, cases, all the three modes are Raman active. Okay, they will be observed in the Raman spectrometer. All the modes will be observed in the Raman spectrometer. Okay, so what about, this is a type of asymmetric type of symmetric top molecule, simple symmetric top. What happened to the other type of molecules? Yes, is there any
Sir?
question?
Yes, sir. Sir, can you
Yes.
please repeat the first one?
First one,
Yes,
which one?
sir. Before stretching.
Hmm?
Yes, sir. This one.
What you want to repeat here means stretching mode. In the stretching mode, what is there? The stretching of the bond. You can just compress the bond, or you can just elongate the bond. Symmetric stretching. It will be symmetric stretch. Symmetric means both of the bond will be symmetrically stretched, equally stretched. Whether it is compressed or whether it is expanded, it will be, both will be equally stretched or compressed or expanded. Okay, during this what happened? This ellipsoid size will change. Okay, polarizability ellipsoid size will change in this mode. Okay.
Okay, sir.
Okay, so this is the one case of the molecule. Another case of molecule can be the CO2. What is observed actually? Why we are discussing CO2 molecule? Actually, in CO2 molecule, only first mode was found to be Raman active. That is V1 mode, new one mode. Other two mode, new 2 and new 3 mode, these were found to be Raman inactive. They were not observed in the spectrometer. So why was that? So we will discuss that actually. CO2 molecule. Linear molecule like CO2. Okay, so again we can just draw the different ellipsoid for the CO2. So, so CO2 is like this. It will be like this. Linear molecules C O O. Okay, and it's this ellipsoid was observed like this initially. Okay, so this is the compressed mode. This is a first new one. Symmetric stretching. So, okay, so now you are just decreasing the bond length. Okay, so what happened? The size will be larger one. Shape will be same. In the third case, we have the longer CO bonds. So in that case, it will be, size will be smaller one. Okay, so here again, what is happening? Size of ellipsoid will change. Okay, what about the second mode? Second mode is bending mode. See what is happening in bending mode. Bending mode for CO2. Okay, so in bending mode, initially the molecules was like this, and bending mode, what is happening is there is angle, some kind of angle is introduced here. Okay, or in the other way we have bended that molecule in the other side. Two different opposite bending is there. Okay, so ellipsoid, it will be initially like this. So when you bend this molecule, what happened actually, the size, the shape will change. Okay, shape will be like this. shape will change. So in that case, what is happening? This molecule was bent lower side and upper side. Both are same actually. If you see, both are same. So shape will be like the same. So equal bending is there. If this angle is, for example, if this angle is some you can say 70, 80 degrees, then it will be same. This angle will be same. Okay, so in that case, what happened? The shape will be same. Okay, shape change is there, but during the bending, although there is changing shape from original position, but in the both the type of bending, what is happening? Shape will remain same. What happened to the asymmetric case? Asymmetric stretching, asymmetric stretching. Again CO2. So we have this original, it was like this. COO, okay. Then we have in one side, we have just elongated the bond. Other side, we have just compressed this bond. In that case, in one side, we have elongated that bond. Other side, we have smaller bond. So initially like this side is like this. So what happened to the shape of that ellipsoid? It will be like longer one, but shape will be nearly same. Shape will be nearly same. Okay, so in that case, you can see that when you are bending the molecule or when you are doing asymmetric stretching, okay, so the shape and size, you can say, of the molecule will remain same. Okay, and further we will discuss this why this is inactive mode. This is Raman inactive mode. This is Raman inactive mode, and this is Raman inactive again. And the first one, this is Raman active. This is Raman active mode. So why this is only one mode which is active, other two mode are inactive. So I will discuss this in more detail, maybe next lecture. Okay, so I can stop here for today. Any questions you can ask?
Sir, is there any, there is no rotation in case of CO2 molecule in
There is
asymmetric
no
stretching. Sir,
asymmetric.
in case of asymmetric stretching,
Mhm.
there is no rotation of ellipsoid.
No rotation means.
So in case of H2O, it was rotating.
Yeah, that's what I will show you. What is the reason behind that? So I will discuss in terms of the, you can see, polarizability and the curve slope. So we will see that whether there is a change in the that polarizability with distance. How this polarizability will change, changing the distance. Okay, so I will discuss this in details. Okay, in maybe next lecture. Why these modes are inactive? We will discuss that in the next lecture. Okay.
Hello, sir.
Yes.
Yes, please.
Sir, I'm not present in the starting class. In this rotational spectrum we are showing in band diagram. That is the first one. Starting is very low, and in going to high level, it will be increasing the increasing that uh, increasing that increasing that levels. But in vibrational, first will be higher, and when we are going to higher level, it will be decreased. uh, how we will understand these two things, sir?
So we have mathematically defined that. If you see vibrational equation and that rotational equation, so we had mathematically shown that actually this will happen. So you can go back to the lectures which we have. I think I have shared this lecture with you, rotational spectra, isn't it? I had shared these lectures with you all. Okay, so go through that expression, these expressions. Mathematically, you can see. Okay,
Sir,
yeah.
sir, one more thing. Sir, is there any chance to take offline classes, sir?
Okay, so yeah, so there is actually some. So there is the room is allotted this in the Porta cabin. This is room number 32. So I don't think there is some AC or fan available. I don't know. So please check that room if it is available. Means if it is good conditions to take classes, I can take there.
In online
Okay.
is somewhat disturbing, sir. Sometimes net is not working properly and the voice
Okay.
also.
Sir,
Okay.
we can take class in 101, sir. 101 is over room, physics department.
So yeah, 101 actually there is another class is happening there no, in the same time, 12 to 1. Or first year class is happening there on this Friday. On Friday 101, the first year class is happening. So actually, the one more classroom is allotted to us, which is in Porta cabin, I think classroom number 32. Please visit there. If it is in good condition, we can take classes. Okay, they are offline.
So
Okay,
32,
hmm?
132 or 32, sir?
I think it is 32 only, 32.
Only 32.
Yeah, classroom number 32 in Porta cabin. See if there is some fan is available or not. AC, I don't think there will be AC. Okay. So if there is if it is in good condition, then I can take the next class in that room. Okay. So the attendance please Alok Kumar Mahanta. Alok Kumar Mahanta. Absent. Anjana Vincent.
Present, sir.
Asghar Ali.
I'm present, sir. Mic was not working.
Who is present?
Alok.
Okay. Then we have Atul Krishna.
Present, sir.
Ramnan Behra.
Present, sir.
Abdul Kalam. Diya Singh.
Present, sir.
Ipsita Biswal. Ipsita Biswal. Absent. Kalpana